So this is the basics of limits from the first section, right? The limit of a function is the value that the function is approaching as x approaches c, which means some constant, or x approaches infinity. It's important. The reason that we're doing this is because sometimes functions don't actually have values for that value. X cannot equal c. But it actually has a limit that we can evaluate. So this idea here that sometimes a limit exists when the function value doesn't exist, that's kind of why we're doing this in the first place. It's totally expected. I mean, if people didn't see this problem way back when, who invented calculus, do you know? You know his name, I'm sure. Come on, you're watching Jeopardy. This guy invented calculus in the 1700s right after he discovered gravity. Isaac Newton, you know, just grab a name out of that general period. And yeah, he's the one, although it is a little contested. There's another guy named Leibniz who was in Germany who supposedly developed it at about the same time. But most people credit Newton as being the guy who discovered that. In any case, if they weren't perceiving problems like this, they would have never come up with the mathematics of calculus. I mean, and a tangent line problem was a good example of why they needed something like this. We would like to be able to find the slope of a graph at any point. Because we've got a real-world function representing real-world relationships. The slope of the graph is telling you how your function is changing. It's called rates of change. And they'll use that term a lot in calculus. I didn't use it that much, but it's a pretty important concept to understand the rates of change. So they wanted to find, we know how to find the slope of a straight line. How do we find the slope of a graph when it's changing its slope at every point along the way? Right, okay, well, we can estimate it by taking 2 points and then calculate the slope, but that's not going to be exact. What if we move the points closer together? Okay, that'll be a little bit better. What if we keep moving them together? Okay, it's getting better. Can they ever come together all the way? They never can, right? Then we'd be dividing by 0. So you can't do that. What you can do is, as you move the 2 points together, write down the slopes and see if it looks like they're approaching some fixed value. And if they are, that's the limit, and that will be the slope at that point. So that solves the tangent line problem. And then the area problem, which we saw at the very end, was we would also like to be able to find the area underneath an irregularly shaped graph. And we're going to do it by putting a bunch of rectangles underneath, and we'll find the area of the rectangles, because we know how to find areas of rectangles. We add them up, we get a value. Is it accurate? Probably not. So we increase the number of rectangles. Right? That makes each one a little bit narrower. The approximation gets a little better, and we can keep increasing. But can we ever let the width of the rectangles go to 0? Can we let there be that many rectangles? No, because then every rectangle would have an area of 0. So what we can do is, as we make the number of rectangles increase, we can write down those areas and see whether there's a trend. Does it look like they're approaching some fixed number? If they are, that's the area under the curve. That's the limit. That's the area under the curve.